Welcome back to this channel. In today's video, we are going to be considering the topic, the Randomized Complete Block Design. Now, what is the Randomized Complete Block Design about? First, it is abbreviated RCBD, or the common parlance, statistical parlance, RBD, which basically means Randomized Block Design. Alright, so now, the major difference between the Randomized Complete Block Design and the former design we talked about, which was the CRD, is the fact that the CRD uses only one source of variation that is controllable by the experimenter. And the other source of variation is the extraneous factor, which is not controllable by the experimenter. While in RCBD, the experimenter has the capacity to control, has control over two sources of variation. One being the treatment that is being applied, and second being the blocking, what is known as blocking. Now, it therefore means that whilst in CRD, the sum of squares total, or the total variation will be the total variability, will be variability due to the treatment, variability due to treatment, and the variability due to the variability due to error. But in RCBD, so this is CRD. Now in RCBD, the total variability is going to be equal to the variability due to treatment plus the variability due to blocking of the block and the variability due to error, that we can't control. The variability due to error, that is the variability within. Alright, so the RCBD applies two sources of variation, while the CRD applies one source of variation. So that is why you will see the format of the question of CRD to be just like this. For example, you are going to have treatment A, treatment B, treatment C. For example, if I want to test for the effect of a particular feed on tilapia, I'm going to be applying the treatment only on tilapia, take note of that. And the treatment will be different, so there will be different feeds. For example, I could be testing with feed A, feed B, and feed C. So the only thing I am varying in this case is the feeds, and those are my treatments. So that is going to be the major source of variation. Alright, so then the other things you are going to have are just your the effect on the experimental units. So notice, alright, but in RCBD, the treatments are going to be here, but I am going to be testing this treatment on, I'll be testing on tilapia, and then testing on clarias, and then testing on Cyprinius carp, and then testing on bar. So notice I have different experimental unit sets that I am testing on. Alright, so this arrangement is the RCBD arrangement, because these factors that are introduced there, these other sets that are introduced there, this other group that are introduced there, is another source of variation, and that is what is called blocking. So notice from what I said that I will be testing these different feeds on the same species of fish, tilapia. So everywhere you find a data set here, it will be with respect to tilapia. So meaning we are considering tilapia. So what does that mean? It means that CRD is used when your experimental units are homogeneous. When your experimental units are homogeneous. So if there is a degree of difference between your experimental units, then CRD is no longer in use. So it therefore means that when there is heterogeneity within your experimental units, then you can use RCBD. Now, what is the implication of this? Remember that in CRD, where we use the same set of experimental units, now what happens is that the error within the extraneous factors, say for example when we're talking about CRD, that we talked about tilapia, we said there are some things such as biological factor like genetic factors that we cannot control, that the experimenter cannot control. So because of those genetic factors, because the species is the same, your experimental unit is homogeneous, then that factor adds up. That factors adds up and makes the error increase. All right, let me repeat that. I said that because of extraneous factors within, because of homogeneity, extraneous factor within, because of being the same group, will add up. All right, but in the RCBD, those extraneous factors that are supposed to add up has been mitigated here. Why? Because the units are heterogeneous. So those extraneous factors don't add up. Of course, there will still be variability between treatments, but there will be no the variability within will have been reduced because of the heterogeneity of the factors. Notice, this treatment A is being applied for tilapia, still being applied for clarias, being applied for Cyprinius scapio, and being applied for barb at the same time. But the error within, because of the variation, has been maximally reduced. That is why with RCBD, there is a higher degree of precision in your experiment. There is a higher degree of precision in your experiment because the error will not add up or increase. In essence, increase. All right. So having known, so this is the format of the question you're going to see. This is the way it is being distributed in most cases. So while here is CRD that you have only the treatment here, and sometimes the table could be placed horizontally such that you have your treatment A, B, and C. If you see it like this, as far as you don't see any other thing on top, this is still CRD. But if you now see another kind of say treatment or any other thing on top, that is varied. If you see any other thing here that is being varied, then that thing is also a source of variation, and then the design is no longer CRD, it will be RCBD. So that is how to identify or differentiate between RCBD and CRD. Okay. Now let's talk about the design. Number one, the model of the design. Of course, we know the name. The name is RCBD. The model of the design is given by Yij equals mu, that is grand mean when we talk about population, plus the tau or tau I plus beta j plus epsilon ij. So the epsilon is the error, the beta is the block. Now, let me explain further what blocking means. So for example, if I want to test for the effect of a particular societal construct on the perspectives of people, I cannot just rank people. I cannot use it to be, my experiment will be defective if I use the CRD to generate my data and analyze and conclude, because although humans are humans, they are the same biologically in a way, but of course there is some degree of biological consistency, but individually, because of exposure and all other factors, they are different. That difference is an intrinsic factor. So, for example, if I will be conducting that kind of experiment, I have to put people of different societal classes together, people that earn low income and people that earn high income should not be placed together. Why? Because their perspectives of life will be different. So, hence, that arrangement into the different social classes, although they are still humans, and there were still fishes there, tilapia, and the other example I gave the other time, they are still humans, but I have segregated enough to make sure that it is only people of the same class that are within the same group, so that the effect will be understandable on them, different from the way it is happening to the first group of individuals. Alright, so that is blocking. And the treatment is, of course, what you are applying and you are basically testing for. Another thing you should know about this blocking is this. Now, you will notice by the time we begin our computation, you will notice that at the end of the day, when we'll be taking our variance ratio, please take note of this, when you'll be taking variance ratio, we don't take the variance ratio of our MS block. We don't calculate the variance ratio with respect to block. Why? Because the only reason why we need the blocking is to ascertain, is to make sure we have a higher degree of precision in our experiment, number one, and also to make sure that our data set is as heterogeneous as possible. Now, if we test, this is the implication of testing for a block. If you test for block and your F calculated for block is greater than your F tabulated, then it means that your analysis of variance is has a high precision. But if you calculate your F cal for a block and it's less than the F tab, then it means that your precision level is very low. Alright, so that is the only effect of that blocking. Alright, so the major thing we are particular about is the treatment. So that is why we will only be calculating the error the variance due to treatment. The F cal for treatment. Right? So this is the model. Now, another thing you should learn is the fact that when calculating RCBD, the steps that you follow. Please listen carefully, The steps that you follow while calculating RCBD is basically the same as CRD. Only that if one more step has been added, and I promise you, throughout all of this course, the basic steps that will be used for calculation are the same. Just make sure that you know those formulas, and I've told you before that they are simple formulas. Only that at each step we add we have further things to calculate, more things to the calculation propagates, right? So it's not that the calculations are not changing, only that we are adding more factors to calculate for, So that is the way it is for RCBD. So remember that what do we start with when we want to calculate for CRD? We first start with this correction factor, and it's given by what? GT squared, that is the grand total square, over what? Over n, that is the total number of observations. Then our SS total next. So we always calculate, please remember, CF, SS total, which is given by what? Summation of each treatment squared minus our correction factor. Alright, this I means that the treatment in the ith observation, right? So then the SS treatment means the summation of the formula is summation of y all squared, that is summation of our treatment that is tau all squared minus correction factor. Now this will be divided by the number of replicates of that treatment. Okay? Now, then in CRD, after treatment, we go to calculating SS error. But the difference here is that we do not calculate error yet. We calculate one more thing, which is SS block. Then afterwards, we calculate the SS error. Okay, the SS block is going to be by summation of the block all squared divided by replication. Now I'm going to tell you the difference between these two replications. They are not the same. Now minus the correction factor. Then SS error is going to be what? SS total minus, because they are remember the formula I gave the other time, that variation, the total variation is equal to variation due to treatment plus variation due to blocking plus variation due to error. So we are looking for the error and you're cutting these two, you simply subtract, right? You simply subtract these two from this, from the total, and then you get the error. So it's going to be SS total minus SS treatment minus SS block. Alright, let me tell you the difference between this replication and this replication. Remember I did tell you that the format of this is something like this. For example, I'm calculating for clarias, for tilapia, for barb. Okay, let's calculate for, let's add one more. For what other strain of fish that let's calculate for? Maybe goldfish. Now look at this. I have blocked this treatment. I have blocked them. It's called local control. This I forgot to mention this. CRD basically uses two fundamental principles, which are what? Randomization and replication. Alright? But RCBD essentially in all cases applies the three principles, which are what? Randomization, replication, and the local control. The local control, and that is the essence of this blocking. It is this local control that we are trying to apply in the blocking, so that our factors, our experimental units, are as heterogeneous as possible. Now listen, I said the difference between this replicate and this replicate is this. Notice, if this table were to be without all of this, if it were just treatments, that would be CRD design, what will happen? We are going to, if I have a data set here, a data here, and I want to calculate the SS treatment. What am I going to do? I'm going to take the sum of this and divide by how many replications I have. And how many replications do I have? I have 1, 2, 3, 4 replications. So that this will be sum of A squared over what? Sum of A all squared over what? Over 4. That will be my formula here. Then minus correction factor, of course. But here, there is a blocking. So what happens? Please listen carefully, The replication for treatment. Let's see, how many times is this treatment replicated or repeated? Let's see, it is repeated 1, 2, 3, and 4 times. Now, this block, how many times is the block repeated? This block is repeated the first time, the second time, and the third time. So what does that mean? It means that the treatments are repeated in block number of times, and the blocks are repeated in treatment number of times. I'll go over that again. The treatments are repeated in block number of times, and the blocks are repeated in treatment number of times. So that this block containing clarias is going to be repeated for the first, is going to be, treated with the first treatment, treated with the second treatment, treated with the third treatment. So for that block, it is going to enjoy 3 treatments. And this treatment is going to be split into 4 blocks. So that the SS treatment is going to be over how many blocks, and the SS block is going to be over how many treatments. I hope you do understand that. I'll take that once again. The treatment comes in block number of times. The treatment is applied 1, 2, 3, 4 times, and blocks experience 3 treatments. 1, 2, 3 treatments. This guy, 1, 2, 3 treatments. This guy. Do you understand that? Right. So now, having done this, when we get to the SS error, when we get to the error, we are done with the first set of calculations, which are for the sum of squares. So the next thing we calculate now is the degrees of freedom, and we always start with degree of freedom total, which is basically everything you have in your data set minus 1. Alright, so this end you wrote here, just put minus 1. You're going to get your answer. Then next, you calculate for the DF treatment. In this case, how many treatments do you have? It's just T minus 1. How many treatments do you have? You have 1, 2, 3. So it's going to be 3 minus 1. And your DF treatment, what? Will be 2. For SS block, for example, SS block, how many blocks have we here? 1, 2, 3, 4 blocks, so it's just B minus 1, alright? Then the SS block, SS error rather, is just the same order, total treatment block error. Do you understand? For CRD, total treatment error. So it is not ambiguous, it is not complex, it's very simple, alright? Then the SS error is going to work the same way it is. The DF block and the DF error. So it's going to be the same way you did it. It's going to be DF instead now. Total minus DF treatment minus DF block. Alright, so the same way we went about this. Okay, now the next case is this. We then calculate the variance ratio. The variance ratio, which is what? MS over what? MS. Okay, before we calculate the variance ratio, we are supposed to get the MS, the mean squares first. The mean squares. And how do we get the mean square? We don't need total mean squares, and I've said why before. We are particular about the treatment, the effect of the treatment. So we are taking only the mean squares treatment. And how do we get that? The mean square treatment is going to be what? SS treatment over DF treatment. It's always SS, sum of squares divided by degree of freedom. That's how you calculate MS. Sum of squares divided by degrees of freedom. So SS block is going to be what? MS block is going to be what? SS block over DF block. Alright? But in this case, the MS block might not be necessary because we don't need the effect of the block. Alright? So I've told you that before. The reason why we calculate the effect of the block is to know the degree of our precision. If F cal for F group for the block is greater than F tab, then it means our analysis has a high degree of precision. And if otherwise, a lower degree of precision. So after calculating our MS treatment, the next thing to do is MS error, which is what? SS error over DF error. Notice they are just alike. SS over DF, SS over DF. Then the next thing we want to do is the variance ratio, which is MS treatment over MS error. And with this, we are going to get our F cal, and then we can conclude at the end of the day. So you see, it's very simple. The first thing you do is take your take your correction factor, then take all your sum of squares, then next take all your DF, then next take your MS. The same way we organize the ANOVA table, right? We're going to be solving a question right now, and I'm going to only do a few explanations, but I would have solved them on the board because to preserve time. Alright, let us consider this question. It says 3 varieties of tilapia are being compared for yield. The experimental pond was divided into 5 fertility compartments, each of equal size. Each compartment contained 3 plots, among which tilapia were randomly assigned. So notice that they said they were divided into what? Fertility compartments. So that is a blocking for the 3 varieties you are testing for. So you introduce the first bias, which is you are testing for 3 varieties of tilapia. So you test different species. So that first factor is intrinsic. So your first your treatment is actually the fact that your first variation, which is treatment, we will consider as treatment, is the fact that they are different species of tilapia. So of course that factor is intrinsic. But yet again, you now control another extrinsic factor, which is the fertility compartment in the pond where you are stocking them. Okay? So it says every other rearing parameters were the same. After 90 days, the yield in kg for each compartment was obtained as shown below. Now you have to test if there is no difference in the yield, in the mean yield of the 3 varieties. Okay? So what do you want to do first? What you're going to do is, I'm going to do the calculation and show you and then tell you what I did later. So what you want to do is take the sum of all the treatments and write them here, here, here. And take the sum of all the blocks and write them here. So the sum of the first block is here, sum of second block is going to be here, sum of third block here. So and then you now follow the other steps that we have highlighted in CRD. Whoa, this took me some time. So listen, look at what I have done carefully. I am going to explain everything from the beginning to the end. Just take care to listen attentively. I said that the first step to take was to take the total of all these treatments. That is, add up all the treatments, add up this treatment, add up this treatment. I write the answers here. Then add up the blocks, add up the blocks, add up the blocks. Now look at this. I put asterisk here. I did calculate it before. I want you to join me in the calculation. So find the answer to these asterisks and asterisk A and asterisk B, and write the answer in the comment section, just for me to know that you are actually following me. So put the answer to this asterisk A and asterisk B, put the answer in the comment section. Alright, then you add up all of this and you get this. 3.3 plus this, you get this. Alright, so then the grand total is now here. And how do you get that? You either sum everything in the block, you get this, or you sum everything in treatment and you get this. So so after taking the grand total, which is the sum of this and the sum of this, you're going to get 450. Now the next thing to do is to calculate the mean. So you can calculate the mean for the treatment. The reason is this: if you notice a significant difference with respect to this treatment, then it means that you would have to calculate conduct a post hoc test, either using any of the post hoc tests, preferably Duncan, that's DMRT, or LSD. So, and when you'll be doing that, you'll be using the means to compare. So that is the essence of doing the mean from the beginning. Alright, so for example, if you do the mean of that one, 156.9 divided by 1, 2, 3, 4, 5 replicates, divided by 5, you're going to get 31.38. Alright, so you can do the means for all the values like that. But the mean for these guy blocks are not necessary because we will not be comparing the means in the blocks. Alright, the next thing we are going to be considering is, so this is how we begin the calculation. We always start with the name of the design, which is here RCBD. RCBD is the name of the design, and make sure to write in full. Don't write RCBD. It's okay to write it completely. Randomized Complete Block Design. Now the model is Yij plus is equal to mu plus tau plus beta j plus epsilon ij. Now the next thing is the hypothesis statements. In the hypothesis, there are two hypotheses that we have explained before. The null hypothesis and the alternative hypothesis. In the null hypothesis, we are saying that now you make sure you tailor your hypothesis to fit the question. You tailor your hypothesis to fit the question. In the null hypothesis, we have that there is no significant difference between the main yields of the three varieties. That there is no significant difference between the main yields of the three varieties. Then, because we are asked to test for if there is no difference in the mean yield of the three varieties. So you have said that there is no significant difference. Then the next one is there is significant difference between the main yields of the three varieties. So we have the null hypothesis, which is no significant difference hypothesis, and the alternative hypothesis, which is the significant difference hypothesis. Now, another way you can state the null hypothesis is to say that the means that we want to compare at the end of the day, that mu1 is equal to, that's mu for treatment 1, is equal to mu for treatment 2, and is equal to mu for treatment 3. And what does this mean? It means that the means are not different. While you say for The alternative hypothesis H sub A, you are going to say that the mu for the first treatment is not equal to the mean of the second treatment, and which is not equal also to the mean of the third treatment. So these are the two ways that you can state the hypothesis. All right. Now, the next is the computation. How do you compute? You remember the steps. I said CF, then SS total, SS treatment, SS block, SS error. That's the step. So here, CF, we have grand total squared over n. So which is grand total, that is 450 squared over n. Here is the total number of observations, which are 15. So you get this and you get that as your correction factor. Then SS total, you square each guy. Square this guy, square this guy, square this guy, square this guy. Square this guy, square this guy, square. Every guy, then you subtract, you add them all up together, and you subtract the correction factor from that sum. So you have this is the square of this is square of this. Then minus the correction factor, we get this 528.40 for 0.4. Then the SS treatment. Now, I told you that the treatment happens, have how many replicates? Have block replicates. So how many blocks have we? We have 5 blocks, so it means that our treatment occurs 5 times. So that's why it is over B. Minus CF. I've told you before that the treatment occurs block number of times, and the block occurs treatment number of times. That is why it's the replicates there. Alright? So here we are going to take the square of these sums, add them all up, divide by the replicate, and subtract the correction factor. And then you have this, then you get 15.96 approximately. Then the next is the SS block. You take the square of all of these values, square of this guy, plus square of this guy, that is all of the sums of the blocks, So you take the square of this guy, the square of this guy, the square of this guy, and you subtract the correction factor, and you're going to divide that first by 3, because the blocks are repeated in treatment number of times. This block is repeated 1, 2, 3. This block is repeated 1, 2, 3. So you are dividing by the replicate. That's 3. Those are three treatments, so that you have this over this minus this, and you get 460.79. Then finally, the SS error is going to be what? SS total minus SS treatment and SS block. Now, what is our SS total? We got 528.40 minus SS treatment, 15.96, and SS block 460.79. Now, at the end of the day, SS error is going to give us 51.65. 51.65. Alright? So the next, since we have gotten to SS error, the next step is to go and calculate all our DFs. The DF total, the DF treatment, the DF block, and the DF error. Alright? So let's do that quickly. Our DF total. The DF total is going to be the total sum of the total observation minus 1. So that is n minus 1, which is 15 minus 1, and that is what? 14. Then the DF treatment, after total, then the treatment. How many treatments have we? 3 treatments, so T minus 1 equals 3 minus 1, which is what? 2. Then the DF block. How many blocks have we as V minus 1? We have 5 blocks, which are 5 minus 1, that is 4. Then the DF error is equal to, of course, the DF total minus the DF treatment minus the DF block. And that is going to give you 14 minus 2 minus 4, and that would be 8. Alright. So this is the DF error. So the next thing we are going to calculate is the MS. And in this case, we need only the MS treatment and the MS error, because we are comparing only both. So the MS treatment is going to be what? SS treatment over. If you don't understand why we are using only treatment and not block, please go back to the beginning of the video. I explained that. MS treatment is SS treatment over what? DF treatment. Alright? And our SS treatment is what? Is 15.96 over 2. Yes? So that becomes here 7.1818. 7.98, right? 98. That is 19, okay. Then our MS error, MS error is going to be SS error over DF error. And our SS error is 51.65 over DF error is 8. So this is basically going to be 6.46. 6.46, that is our MS error. So let's do our variance ratio. So that variance ratio, which is F calculated, is going to be the MS treatment over MS error. Remember, what we are trying to see is if MS error can break, if MS error, if the ratio is not significant, then it means that our treatment does not have any effect. Okay, so FCAL therefore is going to be equals MS treatment was 7.98 and MS error was 6.46. So at the end of that, we are going to be getting 1.24 as the F calculated. Alright, and when you check, if you check the, so let's now check for the F tabulated now. F tabulated. Of course, we are supposed to present our table first, so let's present our ANOVA table. This is the proper layout. This is the ANOVA table. We have our DF, SS, and MS. So what we basically do is we'll write all the values that we have obtained. We just fill them in here. Now this is the most important part of this table, the F tab and the F tab. Now, notice here, how do we get the F tab? You look at on your F distribution table, you look at your error from here. So I am checking the error of 8 under treatment 2. So where they meet here is what I have at 3.84. Okay. So now what did you notice there? You notice that the F tab is greater. F tab is greater than F cap. Alright, so in this case, what will our conclusion be? What do we do? What do we do here? We will accept, because the F tab is greater than F cap, we will accept the null hypothesis, or the hypothesis of no significant difference. Please, if this place is not clear to you, check back the video I made on CRD so that you can be clear on what we do, what we mean by accepting or rejecting hypothesis. So then, here we will reject, because we have accepted the null hypothesis, and it means that we reject alternative hypothesis. So what will our conclusion be then? Our conclusion will therefore be that H0 holds. That is, there is no significant difference between the varieties of tilapia, because that is the only thing we have to test for. Alright, so, and that brings us to the end of this video. If you do have any question, you can reach out to me on 09021416307. This is my WhatsApp line. So do well to ask me questions, even in the comment section below. when you comment, I am going to check those comments and react to them so that the basic essence of the video is that you understand. God bless you. Do well to subscribe to the channel if you have not. God bless you.